Yeah, welcome to Hifi-Apps. I'm Johann Gauss, physicist from Berlin. This video builds on the first video of the player and is about the parameters in the digital room correction. So the prerequisite is you have done a measurement and start now editing the parameters. We start this from the main menu here in this filter option. So here we have our first measurement and can edit it. If you start editing, the app makes two copies of your filter so that you can compare your changes and take always the better one. At the start you can select if the two copies are slightly changed, that you have a start, or can take 2 times the same copy. In this case we take 2 different copies. So copies get the name of the old filter with 0.1 and with 0.2, and if you have done some changes and like one of your versions more, you can copy one in the other one. Okay, that's the main menu. You can go to select here and look which measurements are included in your filter. In our case it's quite trivial because we only have those 2 measurements of the 2 channels we have done. So we have no choice, we must take those 2 measurements. What you can do here is on one hand edit your filter and on the other hand see the results or listen to the results. So here you can load a test song, the small player, and listen to the results of your filtering, and here you can see the changes. Okay, the first one, EQ, is quite trivial. It's a normal Android system equalizer. The advantage of the system equalizer is that you don't need some calculations. It works immediately and people are used to have it. Okay, from here we can edit our digital room correction. So what we see at the first place are a lot of frequency responses, and you get some overview if you hit this information button. In the first time I hide those, and now you can see 2 things. First, the measured frequency response and the frequency response which is used for the digital room correction. They are slightly different because usually you have more measured frequency responses per channel and the app takes the average. Then the app has to take a sort of peak limiting. You can't correct everything. For example, this is a frequency response of 2 small desktop speakers which simply do not have any signal beyond this, say 80 Hertz. So in this case, the frequency, there shouldn't be a correction. You can't make a subwoofer out of them. And you have a different smoothing. You have so-called frequency dependent windowing, which I explain later. And overall you have this target curve which fits in. So you have slight differences between those 2 kinds of frequency responses. So from here you have 2 possibilities. You can change how it looks and change the parameter for the digital room correction. The first one is here. You can select the way you want to show the time domain. So the phase as a raw phase or unwrapped or as group delay, and you can select your minimum phase and excess phase as well and rotate your phase. Next point is frequency dependent windowing. That's a method to improve the measurement of a frequency response. And the main idea behind it is not just to look after the intensities with which certain frequencies arrive at the microphone, but also the time they need from the speaker to the microphone. So the first signal will arrive with the speed of sound, but you get later signals from reverberation, reflection and those things. And our sense of hearing perceives this completely different. Maybe we have inherited that because it was of big interest if we heard, or if our ancestors heard some noise from some animal, from some direction. They had to know, is it the direct animal or is it a reverberation of something else. They couldn't make a weighted average or something. They had to know where this noise comes from. So we have this preference effect for direct noise. And what frequency-dependent windowing does is look after a short travel time between microphone and speaker. So what is a short travel time? Well, this depends on the frequency. And therefore, you get here different windows. So the first kind of short is from minus 90 milliseconds. The center of the impulse response is always at 0 to plus 90 milliseconds. This kind of short is used for a very low frequency, 0 to 34 Hertz. So for this low frequency, 180 milliseconds minus 90 to 90 is short. And if we take the next, for 34 to 59 Hertz, 132 milliseconds is short. And so on and so on. And we end up here with 14 milliseconds for 2.8 kilohertz to the rest. If we want to change this, you can do it here. And then you can see, you can make it always transparent here. You can see the impulse response and see the different windows with their different colors and use those sliders to change it. If you want to change the different frequencies for different windows, you can do it here. You see the first window goes up to 34 Hertz. The second one starts with 34 and goes up to 59 and so on. So this is frequency dependent windowing and it's used to calculate the room response. It wouldn't make any sense anyway to take later reverberations because they become so complicated and statistically so unpredictable that they will change anyway if you move your head a few centimeters. So for the tweeter, you just want to change the first waves in the cabinet of your speakers that won't change too much and don't want to correct the rest which can't be corrected anyway and is taken as reverberation from your sense of hearing, and the same as well at a longer time perspective for lower frequencies. This is for reflection. That's a pure calculational thing. You can click this best button and then the algorithm tries to fit a comb filter to your measurement. So if this fits, which is not the case in that measurement, but if this fits, you have the hint that there's obviously a strong reflection in your room, and it's a good idea to treat this reflection before you start with digital room correction. At last, you can change your target curve, load a host curve, and change something in the layout. So we have been in that dialog, and at the beginning I said that it's responsible for the representation of the curves. So now I should add not only the frequency dependent windowing parameter go in the calculation of the DRC as well. But anyway, the directly connected to the DRC parameter you can set here. If you call this overlay, you first get the possibility to hide some curves you probably don't need, and after that you get selector between 4 groups of curves, because the calculation of the DRC is done in a sense in 4 steps. You start out with a raw measurement data. You can emphasize it if you type this button and then select it. Those are the raw measurement data, smoothed here with a own smoothing for the DRC and averaged over the measurements if you have done more than one per channel. The first step in calculation of those measurements I've here called cooking. So the next measurements are cooked, and the main difference between the raw measurement is that they are peak limited, that they are fit in a way to the target curve, and that they are fitted in a way to the microphone curve, which I'll explain later. After this process I've called cooking, you have to calculate the correction curve. What you want is your frequency response upside down. You have measured a frequency response, you want to correct it, therefore you need minus this frequency response. So simply this curve upside down is a correction. And after subtracting the correction from the measured data, you get the predicted result, which is in this case not the target curve, but it's a result fitted in a good way to the speakers here on my desktop. They just can't produce some signal in the bus range because they are too small, and therefore I've introduced a sorting algorithm for the best possible fitting you can see here. The main idea is to make a compromise between the target curve, that's the classical DRC calculation, and the strongly smoothed characteristics of the microphone and the speaker. So now I take this strongly smoothed microphone and speaker as default and try the best fit to this curve. If I change this to 1, I'm on the opposite side and the fit is done. I can make it here transparent. The fit is done in the best way it can be done to the target curve. So on one hand you can fit to the average just to smooth out those small bumps in the curve, and in the other way you can do the classical DRC calculation according to the target curve. For the classical way it would be better to have a measurement microphone. You can't smooth out everything in a DRC. Sometimes you have waves which just cancel each other on a physical way, and it wouldn't make sense to put much more power in it. Therefore you limit the amount of equalization. Now the default is here 7 decibel, you can change it to 8, you see those dips become smaller, but anyway you lose headroom on your speakers. And you can set the range in which the correction is to be done. Some people don't like to correct the very high or very low frequencies, and you can select a range where the correction is done in mono. That doesn't mean your songs will be translated to mono. It means just the correction on both channels is the same, which could have the advantage that if you have two subwoofers on two channels, they are corrected in the same way that not one gets the whole load for a certain frequency. Next, you can select the target curve from here too, and you have the possibility to edit the target curve. Here you have a short manual for editing. So the first thing you do is to select with one finger the frequency range you want to edit. You see it here. Then in the next step you can make a 2-finger gesture for the bandwidth, and at last you do the correction and save it or undo it. Here other is balance, the normal stereo balance. If one speaker is louder than the other, you can put this in the correction as well. So last thing is access phase, which is not so easy to explain. I hope it's not oversimpled what I'm telling here now, but you have to start somewhere. And in each correction it makes sense to use this minimum phase correction because it's in a mathematical way connected to your frequency response. But in some case the room or your subwoofer reflex channels or whatever store so much energy that not only this mathematically corrected phase occurs, but also another phase which we call excess phase. And this excess phase can be corrected as well, but the correction isn't so straightforward and it can end out in pre-ringing, that you hear something like ch-boom instead of boom. So you should try to select the full correction, but you should have a test listening to the result and decide if it works in your case. If you have stored too much energy in your room, it can't be corrected in that way. The price would be that the pre-ringing is too obvious. So you always have to make a compromise between minimum phase and excess phase. Maybe soft with a bit limited excess phase is the right way. In fact, it's very different depending on the room, depending on the DRC settings, which kind of phase is the best one. But I would recommend to start with full, or make two versions, one with full, one with minimum phase, and listen to the difference. Then you get an idea of it. You get also a good idea of it if you just search in the web after pre-ringing and look some videos where this kind of pre-ringing is shown. Okay, that's it about correction. So I can close this dialog. At the end, you have two possibilities to look at your result. The first one is use this player, select a song. Then you can play the corrected version, you can play the original version. You can play the corrected with the average of the measurements, and you can play that, which I call caricature. That's the correction in the opposite way. So it's emphasized what's wrong in your setting. And if you get an overview where to listen to what's wrong, maybe you can do some improvements independent of the digital room correction. Maybe you can hear some resonances and get an overview where they come from and all that. Okay, the other way is to see the results, and for example you can see the bursts here, and you can play the burst again as caricature, as original, or as a corrected way. If you tap here in the middle, you play it on both stereo channels. If you tap on one side, you play it on one side. And you can get the corrected frequency response. In fact, this is your measured data with digital room correction and the measured impulse response. That's it. Thank you for your attention, and bye.